All right, hello and welcome to the Off by One security stream. So let's see, what do we want to talk about today? So last time I did this, I had Connor McGar on. That was 2 weeks ago. I wasn't able to stream last week because I was at the Hackfest conference in Arlington, Virginia, teaching a course. So I missed that one. I'm hoping in the future, if I'm going to miss a Friday, that I can try to pre-record something just so something always comes out on the same time weekly and keep that consistency. But either way, we'll miss some times here and there. For those of you celebrating Thanksgiving, happy Thanksgiving yesterday. Hopefully you're having a good holiday weekend. For the rest of you, it's Friday. Well, unless you're coming from Australia or somewhere else. Either way, what is our topic for today? So I put a link in the description of this one, and I'll post it right now if I can find it real quickly. It is there we go, this one right there. It's a prerequisite stream that I did for this one. And it's a stream on Introduction to Linux Heap Internals. So you'll get a lot more value out of this stream if you either have the knowledge from that stream or you go and watch it either before this one or after this one, and then go watch this one again. It'll be super helpful for those of you who just need a little bit of knowledge about how heap internals work and what the job of the allocators is and such. Because when you compare it against the stack is very simple in complexity compared to the heap. As we know with the stack, every function call gets a stack frame, and it's built and torn down dynamically by compiler inserted code based on the calling convention. So super simple memory management on the stack. But on the heap, of course, things are more complex because it's dynamic. We don't know how long memory is going to need to stay in use. And I always give the example, like if you open up a PDF document inside a browser window, you could have that PDF document open for weeks and it just stays resident in memory. And then if you change the URL and you go over to the Google homepage, obviously that's a much a smaller amount of memory that's needed. So all of that memory that was needed by the PDF document can be freed. But the question is, what happens to that free memory? How is it managed? Who's responsible for tracking that free memory? And that's kind of what we went into, or I went into in that stream that I did a few weeks ago on Linux Heap Internals. So this one starts off with that assumption being there, that you understand how basic memory management on the heap works. And in this presentation, I'm calling it Introduction to Heap Exploitation because this technique is nothing new. It's quite old. The good thing about it is that it does a couple of things. It gives us a good place to start with regard to heap exploitation, and it's digestible. If you're familiar with stack exploitation, but you haven't done any heap exploitation on Linux, this is a good kind of segue into that world. And then from here, we can build off of this and go further. So this particular technique we do currently cover as like the remedial heap exploitation introduction in the SANSEC 760 course. And as I've said before, this stream is not supposed to be just stuff from 760. Sometimes the topics will be, though, because that's an advanced exploitation course. So the goal is to actually move this out of that course as an introduction. And the way that I can do that and help the community at the same time is by publishing this. And then that way, when I pull the stuff out of that course and do more advanced stuff, more contemporary stuff, that this will be there for anyone who needs it as a prerequisite. So I think that that'll be good. What I want to do in its place is start off with like a T-cache poisoning technique, or something that works in libc maybe 2.33, 2.34, 2.35, like, cutting edge libc memory management or heap implementation. With the heap managers, you've got the older one, like DL malloc, which is Doug Lee's malloc. Then you have PT malloc 2, which has been around for a long time. It's probably going on 20 years that PT malloc 2 has come out, and it's still used. It's still pretty much the default heap manager that you see on most Linux implementations, unless someone has changed that to something like PHK malloc or JE malloc or TC malloc. There's a bunch of different malloc implementations out there, each with a focus on trying to balance performance with security. And then you have Windows, of course, does it their own way. You can't change the way the heap management works on that. It used to be that the front end allocator on Windows was a look-aside list, and then the back end was just a standard doubly linked free list. But then on modern Windows systems, it's the low fragmentation heap working under the segment heap. And in the kernel, you still see look-aside lists being used, but you've got the segment heap and LFH on by default. It used to be that LFH wasn't turned on to manage a specific chunk size unless there were 18 consecutive allocations of that size. But in the kernel on Windows, it's on by default. And there's a lot of security enhancements and stuff that come with that, like 32-bit chunk encoding and other things. But this stream is not about Windows, it's about Linux. So I just wanted to give a little bit of background there as to why I'm doing this particular topic. This one is going to be abusing the lack of safe unlink code being in older versions of glibc. You'll see unlinked code kind of all over the place. It's not limited to heap management. It's just whenever we have to remove an object from a doubly linked list, you need some code to unlink that. And you want it to be done securely. So I use my analogy a lot, which is imagine you have 10 people and all 10 people are facing each other in a circle and we're all holding hands. So you've got 10 people facing each other in a circle, all holding hands. And let's say that I'm one member of that linked list and that I need to be removed. I need to get put back into production. When I do that, we could say my right arm is my forward pointer and my left arm is my backward pointer. If I were to just unlink myself and run off, then the chunks adjacent to me, they're pointing to memory that's now in use. So if we don't properly unlink and tie those outer hands together that are left kind of flailing, then I could get put into production twice. You've heard of double free before probably. Well, what if I get reallocated a second time and I'm already in use? It's going to cause problems, of course. So we need code that removes me from the unlinked list and ties the pointers together that I was pointing to. We need them to point to each other. And we also need to do some sanity checks. We need to validate that someone hasn't compromised the linked list, because if someone compromises the linked list, as you'll see in this demonstration today, we can get a write what where opportunity. So we could write any number of bytes to the destination of our choosing, something like the procedure or the global offset table, so that when a function is called that's dynamically linked, we can get code execution opportunity there. There's other places we can write to, such as free hook and places like that, detours sometimes. Anywhere that a pointer is going to be called, either automatically or something that we can force to be called, we get this opportunity. So it's funny too, because they fix this code that I'm going to exploit, and then more modern techniques come out, more modern heap management techniques. For example, every thread should be able to, depending on the number of cores and the processor architecture, should and could be able to get its own arena, its own heap, basically, because on Linux we call a heap an arena. So if every thread in every process gets its own arena or heap, great. But some of the performance improvements they did, we don't want to have to count on this global mutex that we've got to wait to be available so that we can do something. Instead, we can give each arena its own set of bins, its own allocators, its own Tcache bins to speed up allocations. And they end up repeating the same mistakes that they have in the past, which is always fascinating. So anyway, a good place to go for that is the How to Heap from Shellfish. So Shellfish, How to Heap is a great place that's kept up to date with good theoretical attacks as well as real world attacks. And a lot of times the code is available with it, so you can download it and practice it yourself. But they're pretty complex, especially if you're new to heap exploitation. So I've been talking enough already. I've got some diagrams I'm going to use at the right time, but let's jump into this example here. And again, I'm on my old system that I use quite often here because of my Proxmark reader and stuff, relying on these old drivers. Okay, so I'm in this. If you've taken 760, this should look real familiar. I'm sure most of you haven't, but just in case you were wondering, as I mentioned, this exercise is a remedial heap exploitation technique I show there. So there's this POC, proof of concept program on here called Heap2. And if we run it and I just give it an argument, you could see it says you entered those bytes. Now, obviously, if we were checking to see if there was a command line argument buffer overflow, we would just pass it a large string. So let's do that. So we run the same thing, but this time we wrap it in backticks and say Python -c print a times 100. And when we do that, you can see it just says you entered. It didn't crash anything. But when we change this to 1,000, you see we get a segmentation fault there on the bottom. And that segmentation fault, when we see that, if you're familiar with Stack Overflows, that's what it looks like, right? Just objectively, it looks like it's probably we overwrote a return pointer or something, we caused a crash, but that's not the case. So the question is, well, how do we know that? First off, we're going to use obj dump, which is a disassembler, and we're going to do a -R, which shows us the global offset table or relocation entries. So we run this against the program. This shows us all the dynamically linked dependencies, meaning this program is not statically compiled. It has requirements. So when you want to run my program on your system, you need to load the libraries or shared object, and I need to be able to link that functionality. So in particular, we can see malloc, we can see printf, strcpy, memset. So strcpy is obviously the problem function here because we know it doesn't have a bounds check. And then we see malloc and free being used. So those two functions in particular are heap functions. Malloc is how we request an allocation on the heap. We pass it a size argument, and it returns back to us a pointer. If it fails, if you've ever seen that little code after a return from a heap allocation request or any kind of allocation request, and it says test EAX or test RAX, that's checking to see if the allocation request was successful or not. If it wasn't successful, then it will be zeros, and by testing 0 against itself, it's going to set the 0 flag, telling us that the heap allocation request failed. But if it returns back a pointer, when we do that test of the register against itself, then we won't set that flag, and we know that the allocation was successful, at least we hope. All right, so we still don't know that this is a heap overflow. So let's go into GDB. So we'll say GDB Heap2, and I've got Jeff on this system. I think one of the last ones I did, it was PETA. It's just another extension, a helper extension with GDB that allows us to do things like look at the heap chunks that are allocated, look at the free lists and the bins that maybe have entries in them, allows us to do pattern generation, create ROP gadgets, search for assembly instructions, kind of all those things that we like to have inside our debugger. If you're familiar with Mona on Windows with Immunity Debugger from Corland Coder, that's a very similar style extension. So now we are inside GDB with the program. So I'm going to run the same command. So run, and then we'll say backtick Python -c print a times 1,000. And then we'll close that out. And this time you can see the crash occurs inside int free, right there on the screen, int free. So that's a function likely called by free where we're having some kind of access violation. And Jeff is showing us the exact line where the problem has occurred. We see that we're trying to move into EAX, dereferencing some offset to ECX. So we're trying to go to ECX +4, dereference what's there, and move it into EAX. But look at ECX, info-reg ECX. It holds this crazy value. We don't know how it got that. There was some calculation that occurred that resulted in that value. If we do a VM map, so we're looking for 4945, you can see that 4945 falls in between the heap and this shared object. It's in the wilderness. It's in the big void of unmapped memory. So that's why we're having this crash. How that value got into there, we don't know yet, but we can see this is a problem with some type of heap operation. If we look at our call stack by typing in BT for backtrace, you can see that free, as thought, as expected, called int free. And then we're all the way back to main down there towards the bottom. So again, just validating and proving that this is a heap issue. So the next question we might have is, well, how big is this chunk allocation before the crash is occurring? If I say info functions, it shows us all the symbols that are loaded, but this one ends up being stripped. I'm going to drop out real quick here. And if I say file on Heap2, you can see it says it's stripped down there towards the end. So that means that all the internal functions like main, they've all been removed. So that means if we want to know from where a function is called, we can look at the cross-references. So Jeff has one option in there called cross-references, which shows us who calls a function of interest. So we can say xrefs stir copy, and we can see from where inside a function in the program that stir copy function is called. So that's one option we have. Another thing we're going to use here is Ltrace. So Ltrace is a tracing tool that shows us all the system calls. So we can say Ltrace and then 2 greater than &1 redirect standard error, so I don't get a bunch of junk on the screen that I don't care about. Heap2 is the name of the program. I'll give it an argument. And then I'm going to, that should be enough actually. Let's just run that. So when we run that, you can see all the function calls here, system calls. We see malloc for 512 bytes, and we see the pointer being returned back from the malloc call. So that, since ASLR is off on this system right now, that address will always be consistent. If we turn ASLR on, that address is going to change each time. But we're just teaching a kind of remedial heap exploitation technique, so we're going to leave that off for now. If I show you another example, so for example, we say check sec file and then heap2, you can see it comes back and says there's no mitigations. One of the ones we do in 760 after this one, if we look at that one, so check sec file. This one, you can see all the protections are on that one. So we start off easy, which makes sense, and then we move to making it more complicated and challenging. It's always important to start and build your foundational skills before trying to jump in and bypass all these mitigations. You want to see the delta as like what's changed between having this off and then having it on. Either way, let's go back and run our Ltrace command. We can see that there are 4 malloc calls. And then after each malloc call, I use memset to initialize that data to A's, B's, C's, and D's, and that's for visualization purposes. It allows us to see things when we're trying to learn this stuff much more easily. So there's 4 calls to malloc, 512 bytes each. We see the pointer return back from those calls, and we see that memset is going on. Then down here at the bottom, we see stir copies being called, and we can see that the data is being copied into the second chunk that's allocated, because we see its address right there that I've highlighted. And then below that, it says printf, and it prints out what we entered. And then we free chunk 3, so the third chunk that was allocated, we free that one first, and then we free the first chunk that was allocated. So we see the order in which these things have occurred. Great. So what I want to do now is go in and set a breakpoint on the call to stir copy. And then we want to take a look at these chunks in memory, and we'll look at the metadata as well. If you had attended the former stream that I did where I went into heap internals, I talked about the previous size field and the size field. We also talked about these flags, the least significant bits. The 3 lowest bits in the size field are flags. The lowest one is the previous in use flag. So it tells us whether or not the chunk in adjacent lower memory is currently in use or not. If it's set to a 1, so again, if the size field of a chunk I'm examining, lowest bit is set to a 1, that means the chunk in adjacent lower memory is in use. If it's a 0, that means the chunk in adjacent memory lower is not in use. And that's a flag used by the free function to see whether or not it wants to do chunk coalescing. So that's an important note, because the technique that we're going to do here to exploit the behavior is due to the fact that we can clear that bit and we can lie to the free function and make it thinks it needs to coalesce when in fact it didn't need to coalesce. And I meant to say it earlier, there are two kind of primary categories of heap exploitation techniques targets that we want. One is metadata, going after the allocators and the relevant functions and how they operate. And then the other one is going after data. So if you do something like override a V pointer inside a heap and go after that, that's more of an application data attack versus a metadata attack, which is what I'm doing. All right, so I'm going to set a breakpoint on the call to stir copy. So let's do that. And in fact, I'm going to bring up another window so that I can leave that one up in the background so that we can always jump back over and grab those values. So let's go inside. So GDB heap2, and then I want to set a breakpoint on the call to stir copy. So I'm going to say xref stir copy. No debugging session active. Okay. So normally I would say break main. We can try that. It says not defined because it's been stripped. So some debuggers out there, they know that the argument that's passed to libc start main, like right there in the after program entry, is actually the main function, but it's not going to make any assumptions here. One thing we could do, if we say info functions, this shows us all the dynamically linked functions. Because it's been stripped, we don't see any internal functions, but we see the linked ones. So we could set a breakpoint on the call to stir copy here, and then look at the backtrace to see when it was called. That's one option. There's many ways we can do this. So let me just do that. I'm going to set a breakpoint here. So we'll say break asterisk, since it's an address. And then I'm going to say run AAAA. We hit the breakpoint. So you can see it says stopped at stir copy at PLT. So if I say BT for backtrace, we can see the caller. This address here that I've highlighted is the return pointer to get back to the caller. So since this is 32-bit in this example, if I subtract 5 bytes from that address, that's going to be the call to stir copy, and we can validate that. We'll say copy, and then we will say x/2i, so examine 2 instructions at that address -5. And there you can see the call to stir copy. So I'm going to set a breakpoint on this address then and delete my old breakpoint. All right, so now I have a breakpoint on the call to stir copy. So let's say run AAAA. And now we've hit the breakpoint. So if I want to look at my instruction here, you can see we're at that call right now. So we can look at the arguments on the stack. We can say examine what argument is being passed to this function. So this right here is the destination address where we should be writing where stir copy should be writing the data. If we go back over here, Ltrace showed us that the second chunk that's been allocated is where we're writing the data for the call to stir copy. So we validate that by looking at the arguments. So, okay, let's take a look at this heap chunk before we do the write. So I'm going to say x for examine /20 wx, so that says examine 20 hex words. And we're going to say $, actually, we're not going to say $, we're just going to give it that address. Now, notice if I give it the address that was returned back to us from malloc, it shows us the mem-setted data. So remember, we initialized the second chunk to Bs or 4 2s. What if I want to see the metadata? Well, subtract 8 bytes from this because there's 4 bytes for the previous size field and 4 bytes for the size field. So if we do that again and say -8, there you can see this would be the previous size field, and this would be the size field. Now notice if we look at the least significant bit, it's a 1 because this is an odd number. So therefore the bit is on. Therefore the previous in use bit is set. And we know that to be true because if we look here, we're looking at chunk 2. Chunk 1's currently in use. We haven't called free yet. So that is correct. So just validating that. So right now our data hasn't been copied. If I say NI for next instruction, that means step over the call to stir copy and allow that function to execute and break on the return. So we're going to let that happen. And now we look at that chunk, and you can see that our A's have been written, overwriting the first 4 B's that are there, and also null terminating an extra byte because of stir copy. So, okay, our data's been copied. If I repeat enter and we go down further, you can see eventually we get to the beginning of chunk 3. We see its metadata fields, and then we see the actual data, which is the memset Cs, or 43 hex. So we know it's 512 bytes because we Ltraced it. So if we were to write 512 bytes, we would get all the way down to here, right before the metadata of the 3rd chunk. And that won't hurt anything because the null terminating stir copy byte will just terminate where there's already zeros. So what if I were to write 524 bytes? Then we're going to overwrite the previous size field, the size field, and then go even a little further. So let's do that. Let's see what happens. So I'm going to say run Python -c print a times 512. Actually, let's do 524 here. So we're blowing past the previous size field and the size field, and we'll close that out. And we're breaking on the call to stir copy. So if we look at the before, that's before. And in fact, let's look at the 3rd chunk as well. So this one here, and we'll say examine 20 hex double words, paste there, -8. There's before the stir copy call. I'm going to say next instruction. Now we let the stir copy call go, and you can see we've overwritten now the previous size field, the size field, and some of the data. So if we say continue, this is where we get that same exception that we saw originally inside int free. So now we have, more of a visualization there. Jeff command start is useful when main is stripped out. Great. Oh, GDB is already running. Let me drop out and go back in. Cool. Nice. Yeah, so libc start main. Great. I never executed that command. Thanks. So, okay, let's drop back out again. And so now we know what we know so far, which is that there are all the chunks that are allocated. They're all 512 bytes. There are 4 of them. We know the data gets copied into the 2nd chunk. We've watched overflowing into the 3rd chunk, which then when we continue causes an access violation because we're trying to dereference something that is not mapped. So what I want to do now is show you what normal operation is supposed to look like on the heap. Remember that there are 2 calls to free. If we go back over here, you can see there's a call to free for chunk 3, and then there's a call to free for chunk 1. So I want to show you what normal operation looks like. And I've got a diagram here. This is what we just witnessed. This is the 4 chunks that have been allocated side by side. The sizes are all correct. The data is all correct. So that's what it looks like right now visually. What we want to see next is this. The 3rd chunk gets freed, and then the 1st chunk gets freed. And you're going to see these pointers that appear, the forward pointers and the backward pointers. So I'm going to set a breakpoint on each call to free and show you this. So let's go back over here in our GDB session. And if we pull back up our breakpoint here, that's the breakpoint on stir copy. So I'm going to reset that again. I'm also going to say x/8i for examine 8 instructions, starting from this address. And helps if I put a slash. And there you can see the call to printf. If I hit it again, you can see there's the calls to free, the 2 calls to free that we're expecting. So I'm going to set a breakpoint on each call to free. So let's set one here. I could also set this on the procedure linkage table, of course. So break. There's our first call to free, and then break on our 2nd call to free. All right, we've got 3 breakpoints, 1 on the call to stir copy, and then 1 on each call to free. So let's go, and we're not going to do anything wrong this time. I'm just going to say run AAAA. Okay, breakpoint on the call to stir copy. So we don't need this one right now. We know what's going to happen. Our data is going to get copied into the 2nd chunk. I'm going to say continue. And now we hit the breakpoint on the call to free. So here's where I want to show you something. So we know that the call to free, if we want to look at the stack, you can see right up here, it shows us that 804A418 is about to be freed, and that's the third chunk. We knew that. So let's take a look at it. Examine 804A418 minus 8. There is, I obviously put something in wrong. X/20X 804A218. So there's our data. So when I'm a little bit off here. Let me see something. 804A418, 804A418. There we go. Let me just clear the screen here and look at everything again. Got my breakpoints. We are at the call to free. Great. So if we grab this address, which is the third chunk, and we say examine 20 hex double words at that location, there's our data. Something was syntactically wrong when I was entering. So there's what we expect to see. If we subtract 8 from that, you can see that our metadata appears. This is our previous size field and size field. Now we are on the call to free. When I say next instruction, we're going to step over the call to free. And what you're going to see is a forward pointer appear there and a backward pointer appear here. So I say next instruction. Let's take a look. And there is the forward pointer and there is the backward pointer. Now, currently, they're pointing to the same thing because there are no other free chunks on this heap right now. It's a very simple program. So what they're pointing to is something called, we can refer to it as the Sentinel node. It's inside the main arena. Basically, there are these doubly linked free lists and these different bins that the free lists are associated with. And grouped by size, chunks are put into one or more of these bins. So that's what we're seeing right now. If we were to take this address, if we took this address and we say, let's take a look at it, you can see it says main arena plus 92. And at plus 8 and plus 12 are the forward and backward pointers because it's supposed to be circular. We want it to be a doubly linked list that's fully intact. So right now it points back to the list head or sentinel node that points straight back to itself because there's only one free chunk. So we know what's going to happen next is that free is going to get called on the first chunk. So what we'll see is the backward pointer right here will be updated to point to the first chunk since it will soon be freed and on the same free list because they are of a similar size. Another thing to look at, remember one of the things free is supposed to do is clear out the previous in use bit of the next chunk down. So in case that ever gets freed, we coalesce the chunks together because the rule on the back end heap is that 2 free chunks are not allowed to be side by side and free. We coalesce them into one big chunk to reduce fragmentation. So if we go and take a look at the metadata of the fourth chunk that we allocated, so we'll say x/20wx, start at that address, minus 8. Right there, remember the other ones are 209. This one is 208. That's because free went and cleared the previous in use bit. Okay, so let's say continue. Now we're on the next call to free. And we're about to free chunk 1, as you can see in the top of the stack at the argument being passed. Okay, so let's one more time take a look at the forward and backward pointer of chunk 3. We're about to see this get updated. So next instruction. And now you can see the backward pointer of chunk 3 points to chunk 1. If we go and look at chunk 1, its forward pointer points to chunk 3. And it matches what you see in this diagram here. This is what it's supposed to look like. Everything is fine right now. What we're about to do is take advantage of the fact that this code is missing a check to prevent a write what where opportunity for us. What it should be doing is before we free a chunk, or before we unlink a chunk, I should say, before we unlink and remove a chunk from a doubly linked free list, we should validate that the chunk we're unlinking's forward pointer points back to the chunk we're unlinking, and we should validate that the chunk we're unlinking's backward pointer points forward to the chunk we're unlinking. If we don't do that, there's an opportunity to corrupt this doubly linked free list and get ourselves a write what where opportunity. And that's what we're going to exploit. So let me start that process now. What we're going to do, let me start this over. So we're going to info break. I'm going to delete breakpoints 2 and 3. And now we only have the breakpoint on the call to stir copy. I only set those breakpoints on free so you could see how it's supposed to operate. Okay, so now I'm going to send in 512 bytes to get to the metadata of chunk 3, but I'm going to mess around with the metadata. I'm going to change the metadata for the previous size field to be -4. I'm going to change the size field to be -16. By making it -16, I'm also clearing out the previous in use bit because that's an even value. And then I'm going to create a fake forward and backward pointer. And I've got a diagram to show you why this is going to work. So let me get it set up first, and then we'll talk about it. So we're going to say run, and then Python -c print a times 524 to get us, or sorry, 512 to get us to the metadata of chunk 3. Plus, I'm going to put -4. So hex fc ff. Plus, I'm going to put -16 f0 ff. Plus, I'm going to put 4 bytes of padding. I'll just say pad. Plus, I'm going to put a fake forward pointer and a fake backward pointer. And I will explain all this in a moment. So let's let it run. We're at the call to stir copy. So let's look at chunk 3 first. So examine 20 WX. There's the metadata before I do this overwrite. Now we say next instruction. And now look at the metadata. I've overwritten the previous size field with -4. I've overwritten the size field with -16. I put a 4-byte pad, and I put a fake forward and a fake backward pointer in here. What this is saying is, remember, free is about to be called on the chunk we're looking at right now. Free is going to go in and look at the size field, least significant bit, which is a 0. It's cleared. That means free is going to think it's supposed to coalesce with an adjacent chunk in lower memory. So what free then does is it goes and looks at the previous size field, and it subtracts what should be a positive value there so that it knows how far back to go to do the coalescing. But look what we've done. We've made it -16, or -4, I mean. We're lying to free, so free thinks the start address of the chunk that it's supposed to coalesce with begins here, right there. I have this in a diagram to help explain it. This is what we did. We've overwritten the previous size field with -4. We've overwritten the size field with -16, 4-byte pad, fake forward, and backward pointers. Because free comes in when it goes to free this chunk 3, and it says least significant bit of the size field has been cleared. The previous in use bit is cleared. So it thinks it needs to coalesce. It goes back to the previous size field and subtracts a negative value, forcing it to jump forward 4 bytes. And where that bold red outline is where it thinks the fake chunk begins. And it wants to coalesce it. So it's going to go and grab the forward and backward pointers of that chunk that we now have control of. So let's see what happens. So if I say C to continue, it's going to crash. But now look at the registers. We control EAX, which it thinks is the backward pointer, and we control EDX, which it thinks is the forward pointer. So on this diagram right here, that's what we're messing with right there where it says we control. So our fake backward and forward pointers have ended up in EAX and EDX. Now look at the line of code where the crash has occurred. Examine instruction, where we crashed, move into EDX, which is 46464646. That's our forward pointer. It's saying go to the forward pointer plus 12, which is the backward pointer position, and write EAX. So it's trying to write BK, the backward pointer, to the forward chunk plus 12. That's where we're crashing because it's not a writable address. Guess what happens if we make it writable? We get a write what where. So let's do that. I'm going to go and grab the address of freeze entry inside the global offset table. So we'll say obj dump minus R for relocation entries, heap2 grep for free. And right there, 8049708 minus 12, because remember, it's jumping forward 12 bytes, as we can see right there. So minus 12, 8049708 minus 12 is 80496FC. So let's change this up. 80496FC. So let's think about this. It is trying to write whatever's an EAX, which is BK, to the forward pointer EDX. So we need to change EDX, the forward pointer, to be the global offset table minus 12. So it writes to that location. So let's change the Fs. So F8, 96, 04, 08. So 08, 04, 96, F8. And let's see what happens. So we run it, continue, and we segfault, which we expect. Now let's look at the global offset table entry for free to see if we got to write what where. Examine 804, 9708. And looks like we got a fail here. Let's look at the other direction real quick. Great. So 804, 96F8. 804, 9708. 96F8, 9708. So what I was hoping for right now, let me start this over again, is a write 804, 96F8. 804, 9708. Oh, FC. My math is bad. Not F8, FC, because that would be minus 16, right? This is minus 12. This is why it's always great to do demos live, because the demo gods like to make fun of you and make your life miserable. But I wouldn't have it any other way. I don't like pre-recorded video demonstrations, even though they might save time. Watch this now. We run it, crash, look at the global offset table entry for free, and there we go. We've got 42424242 in freeze entry in the GOT, which means if free were to get called, we would have crashed. So perfect. We've got to write what where. Now, why did it crash now? We'll take a look at the instruction where we're crashing up here. It's now trying to go to the backward pointer plus 8 to write FD. We need to make sure that both directions are writable. If we don't, then we're hitting this crash here. So it's really nice to be able to see the code right there where the crash is occurring. And this is why it's so important to understand how the unlink operation works and what's actually happening under the hood, as opposed to just being told, oh, just type this in and it works. So now you see why it's broken, because we're trying to go to BK, forward pointer, and write FD, and it's crashing. So we need to make sure that both directions are writable. So let's do that. Let's make the other direction, instead of being 42424242, let's make it the buffer where our data gets written, which is 804A210. So 804A210. Let's try that. 10, A2, 04, 08. So let's do it again. So continue, and we crash, but let's take a look at the global offset table first. Global offset table has been overwritten with the address of the second chunk. Great. So now let's go look at the address of our second chunk. Examine 20WX 804A210. And look at that. It wrote the FD pointer to plus 8. So see how we now have a bidirectional write what where? We can write in two directions. Well, why is it crashing then? Let's take a look. Now it's trying to test byte pointer EAX plus ECX times 1 plus 4 against 1. It's trying to test a bit, a value, and it's failing because that calculation right there is bad. So let's do the calculation. So examine byte at EAX plus ECX times 1, which is nothing, plus 4. Cannot access memory at 4945 E544. That's why the crash is occurring, because that's in that void again. It's messing up. Okay, so we've got the write what where in both directions, but the process is still crashing because of this instruction right here. Now let's think about free again and what free is supposed to do. So we've watched it run the unlinked code, and it's updated what it thinks are the forward and backward pointers. One of the other things that free needs to do is check to see if coalescing needs to occur, both forward and backward. So it needs to do a couple things. It needs to check to see if the forward chunk in memory's previous in use bit is set, because not only can we do backward coalescing, we can do forward coalescing. It also needs to update the previous in use flag of what it thinks is the next chunk. So it's got a couple other things it needs to do, and that's where it's failing. It's trying to check to see if the previous in use bit is on or off. And it's failing because that calculation is resulting in a bad value. What ends up being the problem here, if I go to this diagram, is remember that we used -16 for the size field? What it's trying to do is check the flag of what it thinks is the forward chunk. And so therefore we put -16. We need to go back to -16 and make sure when that calculation occurs that everything works out okay. So to fix this, what I'm going to do is go inside here, and I'm going to change the -16 position, to be -1, so that when it does that multiplication, it doesn't end up being some crazy value. So let's think about this for a moment. So if I want to get to -16, that's 12 back. So I'm going to take off 12 bytes here, change that to 500, and then I'm going to say FF -1 plus A times 8. So what I've effectively done, I'm making sure the alignment is still correct so that we overwrite the previous size field with -4 and -16 in a size field. I've subtracted 12 bytes from the A's at the beginning, because at -16 from the size position, which is right here, from -16 from that location, I'm putting a -1 there so that that calculation ends up being okay. You'll see it in the debugger, because what I'm going to do is set a breakpoint on int free plus 173 so we can watch this calculation. So let's run that. We hit the breakpoint, and I'm going to say break at that location, and then continue. We've hit the breakpoint right there, breakpoint hit, and look what it's about to do. Test the byte pointer EAX plus ECX times 1 plus 4. And this time, that calculation is 4-1. So it's fine now. It's going to test to check to see if the bit is on or off. And then we're going to pass this check because that's valid memory. Okay, so let's continue. Look what happened now. We crashed. The instruction pointer crashed at 804A400. That's clearly our lowercase a's, our uppercase a's that have been executed. So we should be able to put shellcode then in the beginning of buffer 2 and have it execute. So if I want to grab the shellcode, so shell cat heap2 shellcode. This is just shellcode here to open up port 9999, I believe. So I'm going to grab that shellcode. And let's bring up our input again. So at the very beginning, I'm going to put this in. It's 84 bytes. So our shellcode is right here. I know I should be putting this in a script, but I'm already in command line. So that's 84 bytes. So I need to subtract 84 bytes from the A times 500. So 416. And let's make sure our alignment is okay. So we'll run this. Oops, what just happened here? Foreground. All right. I want to check my alignment. So let's take a look at chunk 3 to make sure everything looks good. X/20WX minus 8. So our alignment looks, well, we haven't let it copy yet. This is the before, here's the after. Everything looks good, so our alignment's still off. When I say go to continue, we should execute shellcode, right? But look, there's a crash, and it breaks somewhere in our buffer, in our chunk. So let's take a look at the beginning of chunk 2, where our data has been written. So examine 20 hex double words at that location. And you can see our shellcode right there, 31 dB. But right there, oh, we forgot. Remember, it goes back and it tries to update the forward pointer. So it clobbered our shellcode. It overwrote 4 bytes of our shellcode with a pointer that it was trying to update. So what we're going to do to fix that is simply put a little EB0E. I'm going to jump 14 bytes over, and that way we get past the clobbering of the shellcode and we execute the shellcode the way we're supposed to. So to do this, I'm going to go to the beginning here and we're going to put in EB jump short 0E 14 bytes. Why 14? Well, there's 2 bytes for this instruction. 14 more bytes makes it a total of 16. So plus A times 14. This alignment should be good. So that's 16 bytes total, 14 A's and 2 bytes for the jump short and the operand. So I'm going to remove 16 bytes from that A times 400, and our alignment should be good. We run this, and we hit our breakpoint, continue, and it hangs. It hangs because the port should be open. Netstat minus NAT. And there you can see 9999 right at the top. So let's make sure it works outside the debugger. So we're going to kill this. I'm going to grab my exploit code and copy it. And we'll get out of here. All right, let's enter it in. Heap2. Paste that in. And it works. So we have the shellcode execution, netcat 127.0.0.1, port 9999, and we're in. So that would be how that technique works. I'm happy to hang out and answer questions for a few minutes if anyone has any, because I know that's pretty quick to go through that. But hopefully it gives you an understanding as to how we approach this. Now, this, I would say, it's the easiest attack we can do against metadata. There are some easier heap exploitation techniques we can do against the data, but as far as metadata attacks are concerned, this is probably the easiest, but it's also, of course, dated. Like I said, unless you find an old system that doesn't have the safe unlink check, this is not going to work. But it really shows you how to kind of branch out and get into heap exploitation on Linux with regard to the metadata. And then, as I mentioned, going forward, I'll do another stream at some point that builds off of this and do something more advanced. But see a couple people saying cool or whatever. Any questions though? Like, how do we come to any conclusions or such? I tried to set the breakpoints accordingly and show you where the breaks were occurring, where the segmentation faults were occurring. Cool. Thanks, Albert. Yeah, if you don't have any questions, you are free to go. Not that you are always free to go, of course, but hopefully you enjoyed this one. Again, I'll hang out for a couple minutes. I'm not sure what I'm going to do next week or next week's session. I might have a guest. I'm thinking about a couple people that I might have on to do some things. I want to go back and forth between having guests on and showing stuff myself. Charles says, had to step away for a few seconds. Was the value in the middle of chunk 2 being set to -1 because that was being read into ECX for the test instruction? The value in the middle of chunk 2 is being set to negative. Yes, because the -16, it thought it was going forward via a positive value to check the forward chunk in memory to then go and see if the previous in use bit was on, because that would tell it whether or not it needs to do forward coalescing. Exactly. It's yeah, there's also, if you were to watch code execution, you would see an or instruction execute, probably to turn a flag on or off. Great, thanks, Noel. Cool. Well, that's it. I'll hang out for another minute, but otherwise, have a great weekend, and hopefully see you next Friday.